And so I knew I'd be going through some of these a little quicker than some of the others. This one is going to be a long drawn out one, but it should be one, I will try to not make it go too long, because there's a lot of really fun stuff in here that I grabbed. So now I'm going to be an atmospheric scientist for a little while, but at the same time trying to remember that it's part of reflected space. But it's to show you the power of the system and what we can do with it. The aerosol composition is basically combining all of the previous stuff. And the diffuse to global, we can get at that in terms of either doing measurements or in terms of modeling. But we need that diffuse to global to get to this index of refraction thing. And that index is the aerosol absorption. That's really what you hear. Whenever you hear anybody say, well, we need index of refraction, what they really mean is I need to know how much we're absorbing. That can also help with closure studies. The assumptions that we have in terms of size distribution for sky radiance, iteration approaches. It's a lot of words that it comes down to is we can do this a lot. And so what happens when you have a lot of data sets is you start to sit there and go, what can I do with them? And one of the studies we did was, well, let's go to Ivanpah Playa, let's go to Railroad Valley, and let's compute the averages. Let's look at what happens as a function of time. Junga parameter here, so again, small, this is angstrom. Smaller angstrom means larger particle, larger angstrom means smaller particle. Aerosol optical thickness, low values means it's clear, high values means it's hazy. Column water vapor amounts, and as a function of day of year, and it kind of just shows the averages over multiple data sets in each of the months. The histogram, the student just found a lot of ways to look at this, but basically, there's not a huge amount of variability in optical thickness, and that should bother you. So these are all the data we have when we were at the site at Ivanpah Playa, that we have optical thickness, and the range of optical thickness that we have in terms of, this was the 550 nanometer value, ranges from basically 0.03 to 0.25. I can tell you that a cloudy day would be around 2 or 3. But I have no 2 or 3 values. So is Ivanpah Playa perpetually clear? Or is there something else that would give me a case where this would lead to a result that ranges such a small optical thickness? If it's a cloudy day, am I going to do reflected space calibration? If I'm not doing reflected space calibration, will I have a measurement? So this is a biased data set already. These are dates for which we have data. And the dates for which we have data were dates that were clear enough for us to go ahead and make measurements. So realizing that that's where we're starting from, this is essentially saying, on a clear day at Ivanpah Playa, what does the optical thickness look like? And we did the same thing for Railroad Valley. We did the same thing and did them as a function of average over the whole year. And what's nice is it allowed us to get for Railroad Valley and Ivanpah average 550 nanometer optical thickness. That's the derived value from the aerosol inversion. And the angstrom, so between the angstrom and the 550 nanometer, that allows me to infer what the optical thickness is in all of the other wavelengths. So the 2 inputs I need for the radiation transfer code. Average water vapor and average ozone. And we can do it in terms of standard deviations also. You notice that the standard deviation of water vapor is not small, 1.14 plus minus 0.5. All of the others have fairly small values. The ozone is just because it's a noisy parameter, but it doesn't cause much impact in terms of the retrievals. What we did with that was then you look at how you then take those inputs and compute a radiance at the sensor. So that's just to remind you that we take these atmospheric data and we're after a radiance at the sensor. And you can use fire to understand what the impacts might be in terms of how good of an answer and how different you might get on a given day. And this was my old workplace, was located right about here. And there was a fire in the mountains to the north. And you can see basically Tucson, Arizona's here. Here's the fire in the Lotus imagery, and then later in the day, the Lotus imagery. And because we were collecting, we were doing tests of those previous collections and getting average values. Some of the days the smoke got in the way of the sun. This is not normal in Tucson. This was all smoke that was causing that. And then we can do retrievals of optical thickness. And so in the same way as I can take averages over time to see what my dates should look like. So this is typical for Arizona, where we have an increase in the optical thickness in June, August, or July, August, and September. And that's because of the airflow. We don't get much mixing in that part of the year. The air mass tends to kind of just stagnate and just sit there. So you get a buildup. And then you can start to look at what happens in terms of optical thickness measurements on a given date. So this was from June 30th, and we basically exceed the average by way more than a standard deviation. And that gives you an idea that something odd is happening on this particular date. You can also look at what happens in terms of averages relative to the Junger parameter, the size distribution, again going for different months of the year. The averages, and this is the summertime when the smoke was happening. So we would expect values from somewhere between, say, 2.8 to 3.4, and we're getting values of 3.6. And then out here, these are power lines. So that's what's happening. You can start to see that you're getting a much different type of aerosol condition than what you expect should happen. So similar to what I was saying is our goals in reflected spaces, is this different than what we expect? Same thing we do now in terms of making a measurement at a site near my work was, is this different than what we expect? But was it different relative to what you might get from cirrus clouds? In other words, all we do is we prove that we have an odd angstrom Junger parameter, we have an odd optical thickness value. So we have a high optical thickness, and we have a very high Junger parameter. But a large Junger parameter means small particles, and cirrus clouds mean large particles. So we would expect, in terms of, if it was cirrus clouds, we would expect the Junger parameter to drop. If we have a case where we know we have cirrus clouds, and we weren't really seeing that in terms of, relative particle amounts. We have low, and then we have high. So you have a typical Junger parameter, and then all of a sudden you get a drop. That's a cirrus case. So we were pretty sure we were seeing smoke. But here's a difficult one. So now this was smoke off of the California coast. Our test site is back over here. And so we've got, if you notice on this particular day, it's cloudy, but there's also smoke. So the question becomes, are we able to discern, using solar radiometer data, can we get to where we would say this is a smoky day or a cloudy day? And again, are my air budgets going to be good or bad on a given day? And now we're using just the SEMEL data. So this was nice because we had an instrument operating on the rooftop of the Optical Sciences Center. We were collecting data throughout the whole time period. Here's optical thickness, so a very low amount, and then all of a sudden it gets very large. And we're looking at, again, optical thickness, and these are very large amounts here, 0.5, and then it gets kind of clear. And these are from two different dates right next to each other. Here is the 27th, and here's the 28th of October. And so the question becomes is now, is this because of dust from strong winds? Is it because of smoke from the fires? Or is it because of clouds? And both in direct solar and in Allen Cantor. So the Allen Cantor measurements again are going in azimuth at a single elevation, and that allows us to now infer size distribution. So here we have a lot of large particles on the 27th. On the 26th, still have a lot of large particles. And then the 28th, we still have large particles, but then also there's this big bump of small particles. And what's interesting is you can start to also go and look at the retrievals of the imaginary index, and you can see that on the 28th, the imaginary index went up as well. But what was important for me was, it was fun, is I think on this one, did I talk about that? I think I get to it, but this tells me that I probably have smoke on the 28th, and the similarity between the 26th and 27th tells me that really what I have is dust dominantly, and if I have anything, it's not going to be smoke, it'll be ice crystal clouds. What was funny was a lot of the people claimed that they could see on the 28th that they could smell smoke. And so now you start to go, okay, how well do we trust people? The trajectory analysis, though, from NOAA, if you go back and look at the weather data sets, well, that should be further north than what we have. The passive radiometer data showed mostly dust and clouds. So it's a little iffy. Do you believe that that little peak at the small size distribution was really because of dust or because of smoke? The Junger parameter, in terms of what we were retrieving, kept going up. And that's kind of indicative of some features like that. But you basically, again, we go back to what we had here at 3.6, is what we were thinking about for an angstrom or a Junger parameter for smoke. And this is within the typical uncertainties that we would see for that given date. So this is normal, and then this is way smaller. And this would be, then again, ice crystals. The 29th, that's the one where now it starts to get really clear. And remember now on the 28th, there was this bump here, so there was a bit of smoke, and so maybe people had real sensitive smell capabilities. But nobody reported smoke on the 29th. That was the interesting part for me. It was because the news didn't mention it. But that peak at the long way, at the large radius went way down relative to the peak at the short radius, small radius. This is the most dominant smoke signature we've seen. It's the one day that nobody reported smelling any smoke. We really have it in terms of the optical thickness going up. In the angstrom values here, we have ice crystal clouds, but right here in the middle, where you see that angstrom value shoot up near 4. You know, there's really only one way that can happen. So the one day that you have great confidence in the physical data saying this is a really different day is the day that most people that were observing with their eyes and with their nose really didn't catch it. All right, uncertainty sources. So we have 2 more. Should be about 30, 40 minutes. We're in the home stretch for the day. This is remember this, we talked about this one already. Angstrom exponent, we're changing the pictures, and we basically have a case where over here we're showing, and it's really using these data, again, to figure out whether or not we have representativeness. From the atmospheric standpoint, that's really what we're going after with representativeness. So the atmospheric measurements, again, our primary uncertainty is going to be the calibration of the solar radiometer. That will drive all of our other uncertainties. And it's whether, even if you have microtops, if you drop it or you scratch it or something, you'll change its calibration, you have to recalibrate it. It could be real changes in the sensor. It could also be our methodology. We may not have Junger distributions, so that may cause us problems. Changes in the amount of aerosols, and this also will affect the radiation transfer code in terms of what those errors do. So it becomes a big, and it starts to cascade is the real problem. This is the issue that we have. The composition of the aerosol plays a big role. When we were doing the work at the University of Arizona, we basically assumed it was always constant. And then we would try to avoid days where smoke or ice crystals or something else came in that were different aerosol types. That basically created a bias, but also allowed us to have an off, if you saw an odd data point, you could see it very easily. And it also allowed me to know how we were processing. When you have 15 people processing data, somebody may decide, well, when I see this result, I'm going to take that value. And we always made sure they use the same value for the composition. So the calibration method for the solar radiometer, think about everything that's built into that. Things are constant as a function of time. That's the big one. The atmosphere is homogeneous. We know what the air mass is. Beer's law is valid. The instrument's not contributing any errors. That's a real big assumption. There's a lot of, you'll see some of this discussion at the end in terms of what the instrument can do. Variation in the Langley plot. So what I showed you was a really nice Langley plot, nice and smooth and everything else. Instrumental effects, temperature, thermal effects can cause wiggles in that, which then will change the intercept calculation, which will then change the aerosol calculation, which then changes the aerosol inversion, which then changes the ozone, the water vapor, the Junger parameter, and you start to get the idea. and all sorts of things in terms of convection, pollutants, things that can change over time. Best measurements happen on mountaintops, morning before you get a lot of mixing and things like that. So if you're doing Langley methods, there's ways to do it right. There's ways to do it not so right. This is a not so good day. And this is nothing. This just happens when you wake up and you've already set the instrument up and then you process it and you find out that things were bouncing around. You might be able to grab a portion of it and get something from it, or in our case, we would just wait a day and collect the other data set. Another not so good day. Turns out if you do Langley collections, you end up with a lot of not so good days. So it's fairly typical. But again, you can pick out time periods where, if you throw away these data points, you can get something that looks like it's a good fit to the linear line. And in that case, you end up with a pretty good estimate where the optical thickness is stable over time. And you have some variability at later in the day and earlier in the day. So this was a day where you could get an estimate of the intercept of the calibration and feel reasonably confident. And why do we try and do this is, as a function of time, instruments change. So it's a weird one to go back. So, this is basically everything's ratioed to this data point right here. And this is, again, multiple bands from the same radiometer. And what's happening is the filters in the instrument, we basically are buying the cheapest filters we can. They're off the shelf. They're not designed to last. We're pointing them at the sun, so they're degrading. And so as a function of time, the instrument itself is losing responsivity. And this is one of the older ones, so we knew we had this, which is why you would basically go ahead and do calibrations about every 3 to 6 months, because you wanted to take into account this change in time in some of the bands. If you do not have that change of 25%, and you try and treat the aerosols, you're going to get a different aerosol type. You're going to get a different Gimbel parameter. So this is one of the uncertainty sources that we have to be concerned about. A good example is if you only had one date. So I have 2 days here, July 8th, July 12th. Both are reasonably good-looking Langley plots. But the difference in the intercept, they're basically ratioed to an average. So on July 8th, it's 90%, 95% of the average. On July 12th, July 12th is 95%, July 8th it's 70% different. If all you had was the one day, you would end up with a very different answer than if you had the other day and said, well, maybe I shouldn't use this July 8th date, maybe I should even worry about the July 12th date. Maybe I'll go back a few months to look at what my intercepts were doing then, or maybe I'll go ahead and move forward a month and see if I can get a calibration and wait to process the data sets. But what that does is if you get an incorrect optical thickness, then that places things on the curve in odd places, and we're doing a straight line fit. And how that straight line fit is handled can be impacted by, what is your uncertainty in your optical thickness here, and then also if you have, as you see on the left-hand here, this one data point seems out of bed at 870 nanometers. And the problem is that normally it's this 1.03 micron detector that is the problem because of the temperature effects. So at the longer wavelength, you end up with a larger temperature problem than you do at the shorter wavelength. In this case, it turns out that the 870 is, on this date, it's a good fit. On the left-hand side, it's a bad fit. And trying to, again, know this ahead of time is difficult. Is this an incremental effect in the solar radiometer? Is there actually an odd aerosol condition that we should be looking into here? So it's a good example of that concern. And just to put it on one graph, is depending on what I use as the calibration, same date, same data set, I use one set of calibrations, I get the purple line, I use a different set of calibration information, and I get the brown line. And those will give me different Junge parameters, which will then give me different aerosol absorption amounts, it will give me different aerosol optical depths at different wavelengths. Everything starts to couple into this error feeding in on all of my other collections. So what could that mean in terms of what kind of uncertainties can we expect? And what we did here was we took a typical case, the green line, and said, let's go ahead and let's perturb that line based on our knowledge of what is the worst condition. So we know that we might have uncertainties in terms of optical depth of minus 0.02 and 0.01. Those are typical for those wavelengths in terms of percent uncertainty. But I'm going to purposely make them the worst case. I'm not going to randomly distribute them. I'm going to go ahead and say minus 0.02 at the short wavelength, plus 0.01 at the long wavelength, and recompute the Juncker parameter and use that to get my estimate of what my uncertainty might be in the Juncker parameter. And so now what we have is basically a case where you end up with 5% uncertainty in terms of the optical thickness that you would retrieve in those cases. And that's the worst situation that we can come up with. And it's, in terms of transmittance. If you go to random, you end up with a 2% transmittance there at the shortest wavelength and 1% at the longer wavelengths. So now you start to see that we have ways that we can start to parameterize based on what we know of our uncertainties in the measurements, what that would go into in terms of what would be the inputs into the radio transfer code. I mentioned that the instrument itself can cause problems in terms of uncertainties. The instrument is designed only to look at the sun. So if we build it properly, we do the optics okay, we have no stray light, all we see is the solar disk. Field of view should not change. I can make this a very large field of view and it would not cause me any impacts if all I had was the sun and nothing else. If I made it so that it was a full 180 degrees, most of you would agree that that's probably not a good idea because I'm getting all this skylight. And that becomes the issue of the field of view, is the skylight versus just the regular light, is the sunlight that we're trying to get. So in terms of field of view versus aperture for solar radiometer, what we really need is we need an aperture size that defines how much energy we're collecting. The field of view it just goes along for the ride. We don't really want any field of view. We'd rather have just near radiance detector if we build it. But the size of the optics, the power, basically just the radiant flux is all we have to have. Just a tube with a detector at the bottom. But it's almost impossible to build something like that without having some kind of angular field of view as well. And then that becomes the trade-off. You don't want to make the tube so small that the field of view is tiny. Then it becomes harder to point. But at the same time, you end up with stray light problems, and also, if that tube becomes too tiny, then you don't get enough energy through the system. So the goal is to try and just make sure the energy is only coming from the sun. The problem is that we're looking through an atmosphere. And so we have this field of view that is only trying to get the sunlight, but at the same time, we're getting light that's scattered out, and that's not good. That's actually what we're trying to get in terms of the transmittance, but you have light that's scattered in. So it's light that's coming from around the sun. You even have the light that's forward scattered from the sun. That's the biggest error source we have, is most of the scattering will happen in that direction heading towards the telescope. The whole point of this is as we have a finite field of view, we're going to get a measurement that has more energy in it than we should have, which means we're going to get the wrong transmittance. And so you should have a correction for this diffuse light energy that comes into the system. Fortunately, with where we work, we do the solar radiometer data, the Langley plot, if this is your dominant error source, then you have done a really good job. But it's still something that we have to be concerned about in terms of as we move forward, we start looking at 0.5%, kind of 1% times error, types of errors. And it's this boring part of the discussion where, boy, if I could just find that 3% thing, I'd be a hero. Now we're talking about, well, I have to worry about forward scattered light from the sun going into my solar radiometer. And it might be 0.25%, and it's going to take me 5 weeks to write the code to correct it. Let me go see if I can find something else to work on for that 5 weeks. So, solar radiometer is the dominant error source. It's our dominant uncertainty. Impact is on effective bands in terms of the optimal depth of retrieval, but it gives us all of these other impacts. So the solar radiometer calibration really only affects the answers in those 9 or 10 wavelengths that we're measuring. But since we're using those 9 or 10 wavelengths to infer information, all that other inference gets uncertainties as well. Once you have that figured out, then you have to be worried about are things changing as a function of time. And that's pretty straightforward to measure. Even if you have a bad calibration, you can see that happening. The other thing that we have to worry about is the underlying assumption. Do we truly have an angstrom case? Do we have a Jungian case? Do we have spherical particles? Does that power law actually apply to what we're doing? And that becomes something that's a little more difficult to assess because we'll never know what the real answer is for the aerosols. So at some point we have to parameterize them some way in the rate of transfer code. And then the importance of this really depends on your test site. If I go to a bright site, then a lot of this goes away. So it's important for us to know in terms of selecting the dates for which the assumptions might be better, or basically making sure we have the right type of test site to minimize the uncertainties we can't control. All right, home stretch, last 20 minutes or so. Error budget. Remember this one? We just got done talking about, just after lunch at the very start. I'm going to concentrate now, not on ground reflectance and things. I'm going to concentrate on these optical depths. I'm going to concentrate on the absorption. I'm going to talk about angular complex, talk about aerosol size distribution. Don't get excited. I put these up to remind you where it came from. I have it in more detail, so we'll go slower. Both excited, wow, he's going to go fast. We're going to get out here really quick. Or, I'm not catching this. Wait, slow down. But I'm only going to worry about these last 2 columns. Now I'm going to get rid of all these 4 columns here and just talk about the section that's related to the work that I did. And so, to pull out the key parts there in terms of the top level, that gets us to this 2.5%. We have 2.2% from the ground reflectance, 0.1 from optical depth, ignore for absorption, 0.5 for complex, 0.3 for size distribution, ignore non-inversion, ignore vertical, polarization, 0.1%, rate of transfer code 1%, uncertainty 0.2%, RSS 2.5%. All of the red ones are what we're going to talk about now. So, optical depth. So the source descriptor optical depth measurements. These are, again, the solar radiometer things that we've been talking about for the last hour and a half or so. The extinction optical depth, this is the measurement that's made by the solar radiometers. That's essentially caused by the calibration of the solar radiometer. So, the computation of the intercept and how well we can do that. If I have enough days where I have confidence that it's a clear sky condition, and we do comparisons between radiometers, both calibrated at the same location, with the same dates, same location with different dates, different locations on the same dates or nearly the same dates, different locations, all the different combinations and permutations. When we bring those radiometers back together and have them operate, they all agree to 0.5% in optical thickness. Right? And that 0.5% is mid-visible, so it takes into account, again, typical optical thicknesses that we see at the test site. It would be better if I put that in optical thickness units, but for most people that doesn't make as much sense. So the 0.5% is something that makes a little bit more sense in terms of, and there's a spectral dependence there. At the short wavelengths, you have a larger optical thickness. The longer wavelengths, the percent difference will be a little bit higher. But it'll end up not impacting our uncertainty here because when we get to the longer wavelengths, where the percent is higher, the total amount is so much lower that it has no impact on the rate of transfer. And all that has to do with is where these green squares or orange squares end up in terms of figuring out what the extinction optical thickness is. I'm ignoring, again, the ozone case and the water vapor in terms of what I'm doing over here. I'm going to pick wavelengths where I don't have strong absorption. So the extinction is only because of scattering. Partitioning into Mie and Rayleigh. is negligible. And that again is because it's all buried in this. So we were dealing with a bunch of people who what it really would come down to is what is your uncertainty of the Rayleigh scattering? We're assuming we know this one, this is the theory. And so then what it does, it forces everything else to be tossed into how well you know your aerosol extinction optical depth. And then that's related to the calibration of the solar radiometer. And what's nice is when you do the rate to transfer theory, the molecular doesn't have as much of an impact as does the aerosol anyway, so this really makes it the worst case condition if you put all of that uncertainty into the aerosol uncertainty. Now, as I'm doing this, you should again, and I mentioned this earlier, is be thinking does he actually have an error, or does he have a repeatability? And with solar radiometry, this becomes one of the arguments, one of the difficult concepts. We're really doing a relative calibration of the solar radiometer. And so this is a kind of a repeatability. If I use the same method with the same different radiometers and calibrated with different locations, all independent, I get to the same answer in terms of optical thickness. So I have consistency, but we never really know exactly what the right answer is. So the way to truly test this in terms of whether it's an error, in terms of an absolute uncertainty, would be we need to get a much better calibrated radiometer that's absolutely calibrated. We know the exoatmospheric solar irradiance, and we were calculating or measuring the transmittance of the atmosphere and comparing that to what we get with the Langley method. We have tried those things. Our laboratory calibrations are not good enough. The way that we have determined the solar irradiance in the past was somebody took a radiometer that they really trusted, a calorimeter, and his name happened to be Samuel Langley, was the first one to try it, to popularize it. Hence the Langley method. That was the way they did it. Was a calorimeter was used. It was assumed that we do the calibration of the calorimeter, and that then gave us the top of atmosphere irradiance as a measurement based on how we knew that the instrument was working. So we're a little bit of ways from doing this in an absolute uncertainty, but in terms of optical thickness, this matches what the Aeronet group is getting, and they rely primarily on an absolute calibration of the laboratory combined with a Langley method. So there's some consistency there. If we take this 0.5 uncertainty, put it into a range of transfer code, and we don't do it as an RSS, we don't do it as a Monte Carlo, we just say, here are some conditions, let's do it as a sensitivity analysis. The top of atmosphere radiance changes by 0.1% for a typical reflectance at Ivanpah Playa, Railroad Valley. So 0.4 type reflectance. At a lower reflectance, that uncertainty would be larger. At a higher reflectance, it would be a little bit smaller. So this is a site-specific result, but it's based on a non-site-specific calibration of the solar radiometers. So going from the radiometer inherent uncertainty, 0.5% at optical depth, putting that into the rate of transfer code, we had to assume something for the surface conditions. And that's where the 0.1%, it's smaller than 0.1%. All that says is that my surface is not that dominant, and that should make some sense. I'm sorry, my atmosphere is not that dominant, the surface is the dominant situation. Absorption computations. I don't like cheating, but I will use it if it makes my life easier. That didn't come out right. In this case, it's okay. I give you a pass. It's not a problem. And I can always go to wavelengths where I have no absorption. And it's more I want to understand the uncertainty first in the normal case, the broader case, and eventually I will work my way into the absorption regions. For ozone and water vapor, what's nice is the retrievals have improved dramatically. So what used to be a 20% error in ozone and a 50% error in water vapor, we're now into the 2% for ozone and the 5% for water vapor. The 2% will be more dominated by whether or not one of the satellite-based ozone retrievals are available. From the solar radiometers, you're still talking about 20% uncertainty, but if we go to TOMS or OMI or some of these other on-orbit retrievals, they're extremely accurate. That's a nice way to do it. Column water vapor, the solar radiometer approach is 5%. GPS is even better than that. So if you have a ground-based GPS, you can get water vapor retrievals. But what's nice is I'm just going to assume that I'm not worried about them right now. I'll worry about that later on. Aerosol type. The type of aerosol impacts how we do the absorption. And it's really important if I have small particles. Small particles absorb far more efficient than large particles. So if I have a smoke case at Railroad Valley, I'm hurt two ways. One, I'm hurt because the smoke is not my normal assumption for the type of aerosol. I'm assuming dust. The second is my sizes are so much smaller that I'm way off in terms of the absorption by the aerosols. I'm going to assume that they absorb far less than they really do. So my top of atmosphere radiance is going to be way too large. And so my counts per unit radiance is going to be way too small. And I'm going to assume I had a major degradation when all I had was smoke in the atmosphere. So I take all of my pictures and I look at the imagery and I look at my Junge parameter and I look at those and I say, I'm just going to get rid of those dates. And so my assumption here, in terms of the complex index and in terms of the Junge parameter, is based on if I have a typical day at my test site, what type of uncertainty can I expect in the Junge parameter? And what kind of uncertainty can I expect in the aerosol complex index? For dust, you go into the literature and you can find ranges of complex index. And they go from basically 0.005 to 0.01. 100%. Sounds really impressive when you do 100%, but it turns out that that's not an insignificant, it's a 0.5% impact on the top of atmosphere radiance. Just because of two different numbers in the literature. This is an acceptable way to do an error budget. If I can go into peer-reviewed literature and I document that that is where I'm getting my uncertainties, then I have a traceability. If someone has an issue with that, then they have to show me in the literature as well that there is something that demonstrates that my values are incorrect. Or they can go to a measurement, or they can ask me to make a measurement, or we can have discussion as to, no, that was for this region of the world and you're applying it to that region of the world, you do not have traceability. But based on the fact that the original paper was from White Sands, we have pretty good regional understanding of that the values are good. There's been nothing to show that, if anything, the absorptions are less, so we might have a value that's a little too high, but that still would fall within the 100%. So this is what I would call a true uncertainty in terms of an absolute uncertainty of that measurement and the impact it would have in terms of top of atmosphere radiance. The size distribution is based partly on what I just showed you, that if I assume that I have this mistake, the optical thicknesses, and I assume worst case conditions and things like that, what kind of shift do I get in the Junge parameter in that case? And that's where this comes from. So this is all again predicated on how well do I understand the solar radiometer calibration uncertainty, and whether I have a good way to assess that uncertainty. And then you put this 0.3 Junge parameter uncertainty into the radiative transfer code, and you get 0.3% uncertainty in the top of atmosphere radiance. And that's mostly because we're at a bright test site, and what the Junge parameter changes, it changes the size of the particles, which changes the directionality of the scatter, and for something over a bright surface, that doesn't have as big of an impact as the absorption over that bright surface. Ah, this is where that dropped in. Okay. Now, I got a little confused earlier, and somehow this ended up twice, and I apologize. So again, just remind you, since I already talked about it, we went through the process of coming up with averages for the test sites. And what's nice is when you do the angstrom, this 1.05 to 0.42 to 1.22 to 0.3, those values, they ended up being about the same as what we assumed if you went through and did an error analysis. The standard deviation is about the same. And so you can almost say that whole variability really is due to uncertainty in the solar radiometers, if you wanted to make that argument. But you can take those averages, and this is another way to look at, are we assessing the uncertainties properly? At the same time as, do we really care about the uncertainties that much related to the atmosphere? The blue is the squares, in this case, are basically percent difference in radiance for Ivanpah Playa, the red. And that is using the measurements on the given date. And the blue is Railroad Valley. And again, using the measurements on the given date. And then you can also go through the process of taking the averages and using the average atmospheric conditions for those dates as well. And you get a percent difference between using the real data and the modeled data, or the average data. And the variation is only about plus minus 2%, with a couple of outliers. And the outliers are basically at Ivanpah Playa. If I had to guess, it's pollution coming down from Las Vegas, or coming from the freeway. There's a few other outliers from Railroad Valley, which this basically says that I could use average atmospheric conditions for all of the processes. All I have to really do is walk out there, measure the reflectance now at this point. We have enough atmospheric information about the test site that we no longer have to make any atmospheric measurements, and we'll get about a 2% variability in our answer. Well, maybe that bothers you, and the question becomes, does that really change the answer? Here's the calibration coefficients. And there's a lot of different colors and things here, but the blue, that's processed using the measurements on that date. And on several of the dates, we went through and reprocessed them using average conditions, average atmospheric conditions, Junga parameter, Angstrom coefficient, same thing, optical thickness at 550, water vapor amount, ozone amount. And we can do that in this case. This is band 4 of Landsat, so this is the near infrared band, 860 nanometers, which again, you shouldn't think there should be much atmospheric influence there because it's along the wavelength. So this really should make a lot of sense. But the whole range here is 0.1 out of 1.5. So you stop and think that's a little bit less than, it's around 8%. Total variability. But you also notice the total variability is not changing that much between whether I'm using the real case or the modeled case. If you go ahead and figure out what is the difference in the calibration coefficient for each of the bands of Landsat. Again, I have an average aerosol optical thickness at 550 nanometers that's retrieved from the solar radiometer data from all the dates, about 50 days. I have the average Angstrom coefficient, Junga parameter, size distribution, same way. I have an average water vapor amount. I have an average ozone amount. And I'm using the measurements of reflectance on each of the given dates, and I'm putting that into the rate to transfer code and computing a calibration. And on average, for band 2, I'm less than 0.25% different than if I did all of my measurements with the solar radiometer and processed them all through the system and did all that hard work. It's about 0.5% in band 1, 0.5% in band 3, a little bit larger in band 4, band 5, and band 7. What's really frightening is the standard deviations. The variability, the scatter, did not change. So I'm unwilling to say that when I process using the average values that I'm getting the wrong answer. Now, statistically, these all agree. There's no statistical difference between the two cases. So from a statistical standpoint, they're identical. The band 5, 7, and 4, that's water vapor. So that's not a real big surprise. That's all down in because we're not getting a good value for water vapor. This is as clear a case of you're almost doing more harm than good by including atmospheric measurements. So all those people who say that the atmosphere is causing a problem at these sites is really they have it sort of right. It's our problem because we're trying to improve the atmosphere as a measurement. We should just be, and here's the real problem. You need an average value for the site. And you also need to be willing to throw away days that you know are not close to that average, clouds, smoke, things like that. But if you have enough of a confidence, let's say you have a SML instrument that's collected data over a couple of years, and you feel confident that you've now characterized the aerosols. And what's nice is the AeroNet group has shown that for certain regions, that's what happens. Once you set up and you collect, the reason they do not allow many more instruments in is because they pretty much have sampled all the climate types that they know of. So there's no reason for them to add more data sets. There's no reason to add more instruments to their network because they're not getting any added information. Once you have that average, you may not need to do any atmospheric measurements at all if you have the appropriate site. This is another advantage to doing uncertainty, sensitivity, and error budgets. I might now be able to collect data railroad. All I really have to have is a radiometer looking down at the ground. I need no atmospheric information whatsoever.
Kurt, are you not now neglecting the fact that you're only using right days? So you need to know when the atmospheric conditions were clear.
Right.
How do you do that?
So there's two ways that you can do that, and that's the key point is you're either at the site, so you're very late trying to get there, but if you're making reflectance measurements, that's the way to do it. But you can go with a much more inexpensive approach like pyranometer data, sky irradiance data, something that's in the range of to deploy, for instance, a broadband pyranometer. That's a $500 instrument that does not have to be calibrated and is very simple hooked up to a Campbell Scientific data logger, as opposed to a tracking radiometer or a multi-filter rotating shadow band system. So it's one of those simplicity things that you could still get information, but you would have to have an assessment. What's amazing is, and I think it was Yamasan, the pen, I think that the phenology network. We have camera systems all over the place now. And so you can even at your test site put a camera that's web sending or, I can't even keep up with the technology anymore, but you can have imagery that will allow you to do that assessment. And again, that would be far cheaper than deploying a Simel sun photometer at 150,000 US with a transmitter. What's that? Go down to 40 with a transmitter?
The whole package. I think we spent about 17.
That's Australian?
Yeah.
So that's like $10 US?
Probably no.
Ouch. What is that? It's actually more like 500,000 US. So, but it's these types, some of them are just nice thought experiments. They're fun for someone like me. Again, I'm an atmospheric guy. It's odd that I'm sitting here finding ways to get rid of the atmospheric calculations and parameterization, but it's exactly that. It's a neat little result that you just want to stop and go, this really shouldn't happen, but it is. And is there a way that I can use it? And this is now in terms of percent difference from pre-flight, and it's the two situations more visually. And it's showing all of the data, average data. Yeah. So you're using the measurements on site, you're using the average of the measurements. And it just shows that the calculated calibration coefficient has a percent difference from the pre-launch. Again, you get to the longer wavelengths, it's a little bit larger, but you're not seeing really big differences in standard deviations. And it's just, again, we're at a bright site. And that's really the whole takeaway on this is once you go to a high reflectance site, so if you're somebody who is a land remote sensor who loves working with ASDs, or even a geologist and you love making measurements of spectra, and you hate the atmosphere, it drives you nuts, I have now given you an excuse to go to a bright site and have somebody make some average measurements for you, and then you can forget about it. And you can go back to doing what you love to do, which is spectral measurements. And you can make those really well. And if you saw early, 2% of your error is coming from those measurements because of the standard of reflectance. So that might be where we put all of our effort. And do not worry about the atmosphere. And we've done this in a further situation, looking at the total uncertainty, and this is a Monte Carlo run that led to that chart I showed earlier. We're showing in terms of the red dots several bands from Aqua Modus. The idea is that we started doing this on a regular basis where we would start perturbing the inputs, the aerosol type, the imaginary index, the reflectance, the water vapor amount, the angstrom, the aerosol optical depth, and randomly assign new values to those based on what we think the uncertainties are from that previous table we had. And when you do that, then you start getting these types of curves, and the problem is we never need to go back and change the scale because we're dominated by the water vapor uncertainty in several of these bands. But you can still pick out a feature where it kind of drops and goes up. And this is, again, we'll see in the rate to transfer discussion, that's because of the reflectance of the material matches up so that you have no sensitivity to the atmosphere. You know, it's reflectance is tucked in here, and so that shows up. So reflectance is the dominant error source once you get out past about 600 nanometers. Short of that, you're dominated by angstrom. But it's still a very small amount, and if you are changing it, you're only getting a 0.05 of unities. This is uncertainty fraction, so this is 5%. It's a 2% uncertainty because of the angstrom value that you're using down with those short wavelengths. That may not be something that's important for you to have to worry about to basically put a solar radiometer out to characterize all the time. Another way to look at it is when you have 60 data sets. You can stop and go, what's a really good day? And what if I only use those really good days? What happens to my answer? So we went through and basically said, we have these averages again. Let's throw away blindly any date for which any of the parameters exceeds that average by 1 sigma. So either aerosol, ozone, or Jungian. When you do that, out of all those 60-something days, you're left with 12. And a lot of them was the ozone was the one that killed us on this. The Jungian and the aerosol didn't. But you're left with 6 data points. These are the dates that most closely match your average atmospheric conditions. So you're again pre-selecting, and this is more of a sensitivity or it's a repeatability type kind of concept. But when you compute the average, you would think that something dramatic should happen. Either the variability, the variance should go down in all cases, or it should go up in all cases, or the thing should change significantly. But basically what it says is nothing special happened. We got smaller variability at the shortest wavelength, but that's almost certainly because we probably had mixed in there was a better reflected set of measurements than we did the atmospheric. At other wavelengths, we got a little bit larger uncertainty. We got some differences in the spectrum or in the coefficient, but statistically, none of them differ. These all agree with each other from a statistical standpoint. It tells us that we're probably doing okay from an uncertainty standpoint, but it also tells us that we might just be fooling ourselves and we just get the same answer. We have better repeatability, but we still have fairly large error bars for standard deviation. So I'm not willing to say that we've basically gotten to where the repeatability is that good. I think this is really, we have a pretty fair understanding of what are outlier days, and we've self-selected a lot of them because of what we're doing when we're out at the test site, when we're processing the data, and that helps. But it also shows the insensitivity to bad data sets when you get to a large enough set. That's really, I think, what we're seeing there.